I'm sorry, Mr. McCarthy. I'm gonna have to ask you to leave. Your credit just ran out.
One more pull. I gotta win. Jackpot. I need jackpot.
Mr. McCarthy, think of your family.
Oh, the jackpot is for my family. Hey, let me go. Hey, hey.
It's time.
Hi, I'm Laura Hopewell, and welcome to the high-stakes world of statistics. Over the next 2 hours, we'll do our best to pump your brain full of statistical concepts and principles, including how to solve statistical problems, graphical methods of analyzing data, numerical methods of analyzing data, and sampling.
Now we know that statistics can be a really rough ride at times. The Standard Deviants have scoured the nation for all the introductory statistics material you need to know, and then hired some awesome stat professors to help us. You can count on us to simplify this stuff and make it easy to learn, easy to remember, and just a little bit enjoyable.
And since you look like the reading type, we've also included a free video outline to help you follow along. Can this still get any better? I think it can. So, we'll start you off on some of the basics.
Before we get to that, let's pause for a brief public service announcement.
And now, words to grow on.
Hi, I'm Don Most. Welcome to Words to Grow On. You know, when I first started out as Ralph Malph from Happy Days, my father gave me some advice. He told me that a nice suit and a charming smile were no substitute for a firm handshake and good old-fashioned hard work. I think he was right. He also told me that sex was not a substitute for love, and that a college education was no substitute for 7 years of hard labor in a diamond mine. Well, 2 out of 3 ain't bad. Don't let this video be a substitute for going to class and reading your books. Please, don't make the same mistake my father did. Unless, of course, that mistake leads to a silo full of precious stones and a quarter share of the world's jewelry market. I'm Don Most with Words to Grow On.
It's called a statistic. The math is simplistic, you see.
Section A. What is statistics?
A stat is a number, some foods are cucumber. Yeah.
A lot of people think statistics is confusing. They see the formulas and get intimidated. Well, when it comes down to it, statistics is a language test. The math is very simple. You just need to understand the language. To make this easier, we've tried to show the relationship between some of the terms for you on the statistical family tree, which is printed on the insert card that comes with this video. Use it, and ye shall conquer many lands, and also your statistics test.
There are a couple ways for us to look at the word statistics. First, let's think of statistics in the big picture.
Okay, so say you've got a bunch of numbers, or what we call numerical data. Statistics is the science of taking out a portion of that numerical data, studying it, and figuring out what that portion of numerical data tells us about the data as a whole.
This leads us to our second way of looking at statistics, or shall we say, the little picture.
The broad science of statistics involves using smaller groups of numbers to tell us stuff about bigger groups of numbers. These smaller groups of numbers are the statistics themselves. In other words, the broad science of statistics is composed of lots of itty-bitty statistics. It's a classic case of the part making up the whole.
For instance, let's take another look at the big picture. Statistics is a lot like an impressionist painting. When you look at it from afar, you see one thing. But after a closer look, there's more than originally meets the eye.
If you're studying statistics, what you're doing is studying how to make sense of data.
Now that you have a grip on what statistics is, we can look at its components and learn how to use them.
Section B, Statistical Problems.
The science of statistics is ultimately concerned with examining statistical problems. A statistical problem exists when there's something unknown about a population. A population is the group you're interested in learning about.
For instance, if you want to find the attitudes of registered voters, then registered voters is the population you're working with. A population doesn't necessarily have to deal with living things. It can be, well, the ages of rocks, or shoe sizes of teenage males, or number of minutes lying unconscious. It can be pretty much anything, really. It's just the group, animate or inanimate, that you need information about.
For example, meet 5-Card Charlie. Charlie is a notorious entrepreneur who has a reputation of making products that flop miserably.
But he presses on in the hopes of inventing that one product that will allow him to open his own riverboat casino.
Well, Charlie's latest product is a soft drink called Fuzzy Dice Cola, and he wants to know whether or not it will meet with the same fate as many of his previous products.
If Charlie wants to know how much of a success his cola will be, he's faced with a statistical problem. He wants to know what percentage of the population will enjoy the taste of his cola.
Okay, stop right there. What's the population?
Well, like we said earlier, in statistics, the statistical population is the large group of people that Charlie will use to gather his data from.
And who does Charlie want to gather data from? Soda drinkers. So, Charlie's population will consist of soda drinkers in America.
Obviously, Charlie can't get good information about his soda from people who've never tried it, right? So Charlie needs to get the population of American soda drinkers to try Fuzzy Dice Cola, find out their reaction, and draw some conclusions about his cola based on the data, which in this case is the reactions he collects from them.
The data in this case would be the number of people in the population of American soda drinkers who liked the cola, and the number of people who didn't.
The conclusions we draw about a population are called inferences. When you make an inference, you take one piece of data and use it to draw a conclusion about another piece of data.
It's like when your grandmother is trying to get you a birthday present. She might find someone in the store that looks about your age and ask their opinion about something. If the person likes it, your grandmother will infer that you'll like it too.
Oftentimes the statistician, or in this case Charlie, is faced with a population that's virtually immeasurable due to extreme size. There's no way Charlie could get every soda drinker in America to try Fuzzy Dice Cola, then report their reactions to him. When this happens, the solution is to take a sample from the entire population and use this sample to make inferences about the population as a whole. We'll go into sampling later, but for now, let's deal with 5-Card Charlie.
To try and gauge the reaction to his cola, Charlie can use a sample. A sample is a part of the population, in this case, a part of the population of soda drinkers.
Got that? Our population is all the people in America who drink soda. A sample is a randomly selected portion of that population. We take a sample because its smaller size makes it easier to deal with.
In order to solve statistical problems like Charlie's, there are certain things that must be established. These are known as the elements of a statistical problem. There are 5 of these elements.
Wait, let me guess. Air, water, earth, fire, and breakfast cereal?
Nope.
Rain, snow, sleet, hail, and drizzle. Michael, Marlin, Jermaine, Jackie, and Tito.
Just roll the elements.
To solve a statistical problem, there are 5 general steps you have to follow. We'll give you an overview of these steps now, then go into more detail as we move on.
Step 1. Identify the question being asked and identify the population. In Charlie's case, the question is, do you enjoy Fuzzy Dice Cola? And the population is American soda drinkers.
Step 2. Determine the design of the experiment. Will you be able to use the entire population, or will you have to be like Charlie and choose a sample from the population?
Once you've figured that out, you need to figure out the best way to collect data from the population or the sample, be it by survey, field research, etc.
Step 3. Establish the method you'll use to collect and analyze your data. We'll tell you more about data analysis later in the video.
Step 4. Choose a procedure for making inferences about the population or sample. These inferences and predictions center around probability. There are a bunch of ways to interpret data and find probability.
And finally, step number 5. See how reliable the inferences you've made are. So you'll need to set up a way to test the accuracy of the inferences and conclusions you've made.
If you want to remember how to solve a statistical problem, there's an acronym my father taught me before the war. Fly, id, air. I, identify the problem and population. D, design of the experiment. A, analysis of the data. I, inferences are made. R, reliability is measured. Use id, air, and you'll always fly to the roots of your statistical problem.
In this tape and in class, most problems you'll face will have done the first 2 steps for you. You won't have to come up with a question or gather data, so count your blessings. You suckers do, however, have to analyze the data you're given. So, since you won't really be tested on actually getting the data, we'll concentrate on making sure you know how to analyze it, make inferences about it, and check the reliability of those inferences.
Organize, summarize, display. That's right, I said organize, summarize, display. Everything
Okay,
will be okay.
so for the purposes of your stat class, someone has identified a population and a question that needs answering. They've questioned the population, and based on their results, they've amassed data.
We organize data into something that is called a data set. A data set is a group of data, like a flock of geese or a herd of cows. Right now, we are getting into step 3, the analysis portion of solving a statistical problem.
Analysis is one of the lengthier steps in the process, and we'll show you a number of ways to analyze data. In our analysis, we'll be doing what is called descriptive statistics, because we'll be using statistics to describe the characteristics of our population.
So, we've got a population, and we've got a question that needs answering. Some poor chump has collected all of the data, and now a statistician, you, is left with a set of numbers representing some sort of information from the sample or population. These are called our data sets.
Let's take a look at an example. Welcome to the National Martyr Competition. Today, the Seniors Competition. In the old Illinois Farm Boy division, grumpy old men compete to see who had to walk the furthest through 3 feet of snow in order to get to school. As you can see, the competition is fierce. Look at these martyrs compete.
I walked 15 miles. 17 miles.
Nuts to all of you. There was a year when I lived in Illinois and went to school in Denmark. I had to walk through Canada, across the Hudson Bay, over the North Pole, down through the North Sea. It was 4,806 miles each way.
In this example, the data set will be made up of the number of miles each grumpy old man walked to school. In case you're wondering, our population is grumpy old men, and the question we want answered is, how far did you walk to school through the snow?
Once you've gathered your data, you need to find a way to present it. We'll show you how to do that in
Section A, Graphical Methods.
The first method of presenting is to use a graphic display. The type of graphic display most likely used in your statistics class is called a relative frequency histogram.
Other types of graphic displays include the bar graph, pie chart, scatter plot, and stem and leaf display, some of which we'll use more often than others.
The ones we'll tell you about in this video are the relative frequency histogram, distribution curve, and the stem and leaf display.
We'll start with the relative frequency histogram because it's the most important. You'll see why as we move along.
This is what a relative frequency histogram looks like. What a relative frequency histogram does is divide the data you've collected into intervals, otherwise known as classes. Then we put the data into those classes, and what we end up with is a box-like display of our data.
If the numbers in your data set range from 1 to 100, you might want to have each class contain 10 units. Your first class would contain 1 through 10, your second class 11 through 20, etc. Keep in mind these are just generic units. Once you've found what units your classes contain, you can line up the values in your data set and put them into classes.
For example, and this is entirely hypothetical, the grumpy man who walked 2 miles would be grouped into the first class, the one with boundaries of 1 and 10.
We're going to go into a ton more detail in a second, but we just want to show you how these things work right now.
Statistics! When you think about it, classes and their boundaries work a lot like bookends around books on a shelf, or goons around a casino boss on the casino floor.
After we create classes for the data and slap our data into those classes, we can look at the number of individual pieces of data that fall into each class. That way, we can see what proportion of the data falls into each class. That's why we call it the relative frequency histogram.
Normally, statisticians use between 5 and 20 classes, depending on how many individual values the dataset contains.
Where you decide to place your classes is entirely up to you. You can start anywhere you like.
Anywhere? But I'm indecisive.
Well, don't worry. There are certain requirements your classes have to meet, and you can use those requirements as guidelines. We'll tell you about those requirements as we go along.
Once we've decided where to put our classes, the data collected from our sample is organized and represented graphically.
It's important to understand the histogram now because of its relationship to the distribution curve, which is what statisticians use most often when representing data. The distribution curve is essentially the same thing as a histogram, only we use it with bigger data sets, and it usually looks like a bell, not a bunch of boxes.
There are 6 basic components to the relative frequency histogram. They are classes, class width, class boundaries, class frequency, class relative frequency, and probability.
Let's start by setting up our classes. We talked a little bit about classes earlier in the video. Like we said, when you determine the number of classes in your histogram, you'll probably wind up with somewhere between 5 and 20.
Let's go back to our martyrs.
After talking to all the martyrs, we can amass the following dataset based on how many miles each man walked to school. Our dataset has values of 2, 5, 6, 6, 8, 11, 12, 15, 17, 19, 21, 23, and 4,806. 4,806 is what statisticians call an outlier. We'll tell you more about outliers later, but for now, just know that because it's an outlier, we're going to exclude it from our dataset.
The data set we've built now contains 12 figures. Next, we need to figure out how many classes we need. To help figure out what number of classes to use, it's a good idea to calculate the range.
The range is calculated by subtracting the smallest value in the dataset from the largest value in the dataset. Therefore, in our example, we subtract 2 from 23, giving us a range of 21.
According to these numbers, I should throw my lasso now.
Boy, Garner took my daggum calculator.
Knowing the range can help us figure out how many classes to use. Take our example data set.
The values in our set start at 2 and end at 23. We can put class boundaries on any of the numbers in between.
If we decide on too few classes, then we may not be able to convey important characteristics of our data set.
For instance, if we create only 2 classes, we'd put the boundary between our classes at 12.5 and split our data set down the middle. Do you see where we got that? We started out at 2, our lowest value, and went up 10.5 to the midpoint of the range. Values that are very different in size are lumped together. If we've only got 2 classes, 15 is in the same class as 23. The histogram is too vague.
It's kind of like someone coming up to you with a world map and asking to see Moscow and New York. Only, instead of showing them the cities, you only show them the countries that the cities are in. Your information just isn't specific enough.
Since people will use our histogram to make decisions based on our data, if they can't discern anything from the histogram, its usefulness is lost.
However, if we create too many classes, empty classes may result. Like too few classes, having too many classes can prevent us from conveying important characteristics of our data set. This happens because we end up with empty classes, which makes for an inefficient way to break things down.
For instance, say we take our range of 21 and break it down into 250 classes. The classes will be really tiny, and most of them will be empty because we only have 12 values to include in those 250 classes. Once again, our histogram becomes misleading.
Even though we have 12 values in our data set, since the value 6 occurs twice, essentially we're only working with 11. Since we're working with 11 different values in our data set, let's divide our histogram into 11 classes. That way we can be sure to avoid empty classes.
Next up, we need to determine class width.
The definition for class width is pretty simple. It's how wide the classes are. In other words, if your first class starts at 1 and ends at 10, and your second class starts at 11 and ends at 20, your classes are 10 units wide.
To determine what the class width will be, divide the range by the number of classes you want.
Remember, the range is found by subtracting the lowest value in the data set from the highest value in the data set.
Using our example, we divide the range 21 by the number of classes we want, 11, giving us a class width of 1.909.
If you try calculating class width and you don't get a whole number, it's okay to round up to a number that's easier to work with. Since it's hard to make an interval 1.909 units wide, let's go ahead and round up to 2.
Whether you round up or not, all classes have to be of equal width. Why? Well, because that way we can make an accurate comparison of the measurements.
Once you've calculated the class width, the next step is to determine class boundaries. Class boundaries are where a class begins or ends. They're kind of like the borders of a state. Where you put your class boundaries essentially determines where you put your classes.
There are 2 conditions your classes have to meet. 1, your lowest class has to contain your lowest measurement. And 2, none of the measurements in the data set should fall on any boundaries. Keep in mind each class will have a lower boundary and an upper boundary.
If you're making a relative frequency histogram and there's absolutely no way you can avoid having a measurement fall on a boundary, technically it falls in the class to the right. However, you should only do this as a last resort.
Here's a quick list of other things you should do only as a last resort.
Let's go back to the martyrs. Stick the lowest class around the lowest measurement and go from there. To do this, we pick a value for our lower boundary. Let's say we use 0 as a lower boundary for our lowest class. Now take 0 and add the class width. The value we get will serve as the upper boundary for our first class. 0 and 2 is 2, so 2 is our upper boundary. Since we have both boundaries, we have a class. Now check to make sure it meets our 2 conditions. Does the lowest measurement fall into this class?
Well, the lowest measurement in our data set is 2, and it falls in this class. But condition 2 asks us to see if any measurements from the data set fall on the borders of our class. Our class goes from 0 to 2, and our lowest measurement is 2. So the second condition isn't met because our measurement falls on the boundary of the class. We therefore can't use the class from 0 to 2.
There's an easy way to ensure that all these conditions are met when choosing the number of classes, the class width, and the class boundaries. Just add another significant digit. It's a trick that works more often than not. When we say significant digit, we basically mean the number of decimal places we use. The more significant digits we use, the more accurate our data is. The value 3.1 contains 2 significant digits, 3 and 1. The value 3.15 contains 3 significant digits, 3, 1, and 5, which makes it more precise. By the way, 23 has 2 significant digits, but there's nothing noteworthy to the right of the decimal place. Except maybe that Gila monster. Let's look at our example.
The first measurement in our data set is 2. This measurement contains 1 significant digit, 2. Some might say that it has 2 significant digits, 2.0, but we'll let it slide and say we're only working with 1 significant digit, and that significant digit is 2.
You heard the man. Let it slide.
The measurements in our data set contain either 1 or 2 significant digits, but none of them have anything other than 0 to the right of the decimal place. Therefore, if we add a significant digit to the right of the decimal place to define our classes, there's no danger of any of our measurements falling on a class boundary. How's that work, you ask? Well, a measurement of 3.0 can't land on a border that's placed at 3.1, right? See how it works in our example.
Since a starting point of 0 doesn't work, we'll just try starting the first class at 1.5. That way, we can set up our intervals and be sure that our 2 conditions are met. The lowest measurement falls in the lowest class, and no measurements fall on any boundaries. Notice how there are no empty classes.
Looking at our budding histogram, the first class contains distances between 1.5 and 3.5. The second class has values that fall between 3.5 and 5.5. The third holds numbers between 5.5 and 7.5, and so on, up to 23.5. These are the classes we'll use to classify our data.
Now, why did we start our first class at 1.5? We've got 11 classes and a class width of 2, right? If we'd started our first class at 0.5, our 11th class would have ended up at 22.5. We would have needed a 12th class from 22.5 to 24.5 so that our highest measurement, 23, would be in a class. But we only want 11 classes because we don't want any of the classes to be empty. So we just avoid the hassle and start things out at 1.5.
Once we've made our classes, we can calculate the class frequencies and the class relative frequency.
The class frequency is the number of measurements that fall into each class. Each class has its own class frequency. The class frequency of our histogram is relatively simple. Each of the classes has a frequency of 1, except for the class between 5.5 and 7.5, which has a class frequency of 2.
The class relative frequency is basically the portion of the total measurements that fall into a certain class. Like the class frequency, each class has its own relative frequency. To find it, simply divide each class frequency by the total number of measurements. So, for 10 of our classes, the 10 classes which each contain only one value, to find the class relative frequency we take 1 and divide it by 12. And for one of our classes, the one with 2 measurements in it, we take 2 and divide it by 12. So, 10 of our classes have a class relative frequency of 1/12, or 0.083. And one of our classes has a class relative frequency of 2/12, or 0.166.
So just to make sure we understand the difference between class frequency and class relative frequency, let's go over them one more time. Class frequency is the total number of measurements that fall into each individual class. Class relative frequency is the number of measurements that fall into each class in relation to the total number of measurements.
Now that we've worked out the details for our classes, this set of information is what we use to form our relative frequency histogram. Let's see how it looks.
To create the histogram, rectangles are constructed over each interval or class, and each axis needs to be properly labeled. The horizontal axis gets labeled with the class values, and the vertical axis gets labeled with the frequency values.
Statistics! The height of each rectangle is equal to the number of values that are in that class. That means the height of each rectangle is equal to the class frequency.
Let's take the interval from 5.5 to 7.5. Since the class frequency is 2, the height of that rectangle will be 2.
When we figure the height of our boxes, there's not really a specific unit we use. Again, the height of the box is equal to the number of values in each class. So let's just say the height is measured in units. If there's 1 measurement in the class, it has a height of 1 unit. If there's 2 measurements in the class, then it has a height of 2 units. If there's 3 measurements in the class, well, you're halfway to a tower. Build on, noble architect.
The relative frequency histogram for our set of walking distances looks like this. It's a pretty simple histogram, but it does the job.
Earlier on, we mentioned that the histogram formed a sort of skeleton for the distribution curve. A distribution curve represents the findings of the dataset just like the histogram, but it does so using a curved line instead of rectangular boxes.
Here's how a distribution curve for our data set would be formed.
If we draw a continuous line to represent the height of each class, or each class's relative frequency, we end up with a curved line as you see here. This curved line we formed is the distribution curve for our set of walking distances.
As far as distribution curves go, this one is pretty simple, but it's a nice introduction to the idea of a distribution curve, and it's quite lovely, don't you think? So, now that we've looked at how to construct a histogram, you know the basis for the distribution curve.
For the rest of this video, pretty much all of our examples will use distribution curves.
We still use more or less the same concepts. It's just the design of the graph that's different.
A lot of what we're covering right now is the setup for the rest of our material, so make sure you got the basics covered.
Let's review how to build a relative frequency histogram. You need to follow a number of steps. First, you need to gather up all the values in your data set. Then, find a range of those values by subtracting the lowest value from the highest value. Once you've found the range, you want to divide your histogram into classes. The number of classes is up to you. Just make sure there's not too many or too few. Once you've determined the number of classes you want, find the class width. To find the class width, divide the range by the number of classes you want. Once you have the class width, you can use it to find your class boundaries. When you choose your boundaries, make sure that the lowest measurement from your data set is in the lowest class, and that no measurements fall on any boundaries.
Once you've created your classes, take the values from your data set and put them into their respective classes. Once you've done that, you can find class frequency and class relative frequency. Class frequency is the number of measurements that fall in each class, and class relative frequency is the number of measurements that fall in each class in relation to the other classes. To find the class relative frequency, divide the number of measurements in a particular class by the total number of measurements. And that, my friends, is how you make a histogram.
From now on, when we discuss, represent, and analyze our data, and subsequently do our analysis, it will be in the form of a curved line.
The graph you see here illustrates what is referred to as a normal distribution, which is nicknamed the bell curve, or in some circles, Skippy.
Just so you know, not all distribution curves are quote-unquote normal. They're not always bell-shaped. Some of them are what we call skewed, and look like this, or even like this. But in your stats class, most of the distribution curves you use should be normal.
Both relative frequency histograms and distribution curves give us a visual representation of data, but we use a relative frequency histogram when we have a smaller data set and a distribution curve when that data set gets larger. There's not a specific sample size that tells us to switch from a histogram to a distribution curve.
We'll learn more about the bell curve when we get to the next section on numerical methods, and we'll see how it works with probability in the high-stakes world of statistics Part 2. So far, we've seen relative frequency histograms and distribution curves. The next graphical method of describing a data set is through what we call a stem and leaf display.
The stem and leaf display is a lot like the relative frequency histogram in that it serves as a picture-like representation of your data. And, like the relative frequency histogram, it shows us the frequencies and the shape of the distribution. It even shows us class frequency and class relative frequency.
But unlike the relative frequency histogram, which measures the proportion of measurements which fall in each class, the stem and leaf display allows you to retain the actual observed values or measurements of the data set. That's because in a stem and leaf display, you don't use a line or box to represent the numbers. You just put the numbers into a pattern. Let's look at an example.
Meet Herb. Herb is an avid hockey fan and recreational gambler. Herb and his friend Mike hold season tickets to see all the home games for the Medicine Hat Fur Traders. Every game, Herb and Mike make a bet on how many goals the Fur Traders will score. The loser of the bet buys the nachos.
To try and win more bets, Herb consults his hockey annual before each game to check and see the average number of goals per game allowed by the opposing team's goalie.
Let's use all the goalies' goals against averages. That's the average number of goals each goalie allows per game to construct a stem and leaf display and help Herb win some free nachos.
Okay, when you're creating a stem and leaf display, each measurement in the data set, or each number, is divided into two parts, a stem and a leaf.
In our current example, we can separate each value at the decimal point, so that whatever comes before the decimal point is the stem, and whatever comes after the decimal point is the leaf. This is easy, right?
Here's a list of all the goalies and their goals against averages. On this list, we have the goalie's name, the team they play for, and their goals against average. Our goals against averages are as follows:
3.94, 2.86, 0.46, 3.02, 3.23, 6.82, 1.47, 5.46, 7.16, 4.73, 3.79, 6.39, 4.04, 4.28, 6.95, 2.33.
To build our stem and leaf display, the first value in our data set, 3.94, would be separated so that the 3 is the stem and 94 is the leaf.
When you make a stem and leaf display, how you break up the values is up to you.
It's sort of a similar thing to when we're rounding off our class width. We pick the method that's most convenient. There may be several other ways to break up the values. We could have put only the number in the hundredths place in the leaf, but again we chose to break the values at the decimal point because that makes the most sense for our example.
To construct a stem and leaf display, vertically list the stems of the dataset in ascending numerical order from top to bottom. So we'll put the whole numbers, the numbers to the left of the decimal point, in that column, with the smallest on the top and the largest on the bottom.
Next, horizontally list each corresponding leaf in ascending numerical order from left to right. What you're doing is taking all the decimals that go with that whole number and placing them in a row from lowest to highest. The smallest goes on the left and the largest goes on the right.
Smallest on the left, largest on the right.
In this method, the stems work like classes, with their leaves showing us a picture-like representation of the data. The picture is formed by the number of leaves per stem.
In a sense, it works a little bit like a histogram, only flipped on its side.
When you make a stem and leaf display, it's usually a good idea to include a key which shows how the measurements are broken up.
The purpose of the key is so that, if needed, you can reconstruct the dataset by just looking at the stem and leaf display. If you take something apart, you want people to know how to put it back together. The key for our display would look something like this. Stem 3, leaf 94 equals 3.94. Pretty easy to crack, even without the decoder ring.
The result of the stem and leaf display for the goals against average example looks like this.
As you can see, this type of graph provides an easy-to-read, easy-to-use table of data. Note that the key at the bottom indicates how we've separated the measurements at their decimal points, so people know how to put the data back together.
With his new table, Herb always knows the score, and he always gets his free nachos.
Oh, that play was a beaut. Let's look at that one again.
First, gather your data set and decide how to break up the measurements into stems and leaves. Next, list the stems in ascending order in a vertical column. Then, take the leaves and list them in a horizontal row next to the stem they belong with. Make a key so people can decode your stem and leaf display, and you're ready to go.
Say we had a league of 70 teams instead of 16. That would mean we'd have to fit 70 goals against averages into our display, and that would drastically change its composition.
Since there are so many leaves with each stem, it creates a similar situation to when we didn't have enough classes in our histogram. The display just isn't specific enough. Since most of the values are clustered around a few numbers, we can separate the leaves even further. Here's how.
To spread things out, we create 2 rows for each stem, so that way we can have 2 rows of leaves. In one row, we put the leaves beginning with digits 0 through 4, and in the other row, we put leaves with values beginning with digits 5 through 9. Now we have a display that is easier to read.
The stem and leaf display is very common in the study of statistics, especially in industry and quality control. Though the distribution curve will be our distribution of choice for the rest of this video, it's important you know what stem and leaf displays are in case you run into them in your class. So all the data displays we've just gone over are graphic in nature.
However, the methods we're about to show you don't rely on any sort of visual representation of the data.
Section B, numerical methods.
This is just a vocab thing, but when we're using numerical methods, if we're working with a population, the things we're finding are called parameters. If we're working with a sample, they're called statistics. P&P, S and S. In general, we'll be using statistics to estimate parameters.
There are 3 types of numerical methods: measures of central tendency, measures of variability, and measures of relative standing.
Measures of central tendency.
Measures of central tendency are measures which describe and locate the center values of the data.
There are three main measures of central tendency. They are mean, median, and mode. Let's meet the three measures of central tendency.
The first measure of central tendency, and the one we use the most often, is called the mean. Now, the mean is nothing more than the average of the values of the data set. Here's how to find it.
To find the mean, take all the measurements in your data set, add them up, and divide by the number of measurements. It's really easy, so don't make anything more out of this than it is. It's just an average.
There is a distinction, however, in the symbols we use to identify the mean for a sample and the mean for an entire population. Remember 5-part Charlie? A population is the entire group we're interested in learning about. In his case, all the soda drinkers in America. A sample is a portion of that group. In Charlie's case, the portion of soda drinkers that he had try Fuzzy Dice Cola. We assume that our data from our sample is applicable to our population as a whole. The mean of a sample is identified as what we call X-bar, and it looks just like this.
The mean of an entire population, on the other hand, is identified as the Greek lowercase letter mu.
In general, we can use the sample mean X-bar to estimate the population mean mu.
Okay, right now we're about to show you the first formula we'll use when practicing statistics. Some of these formulas can look pretty intimidating at first. Don't worry. When you break it down and look at what each symbol means, it all makes perfect sense.
You're about to see the basic formula for calculating mean. We use different formulas to find the mean, depending on what kind of distribution we're using. But this is the one it all comes back to. So if you comprende this one, you'll end up happier than a cat being scratched in a bucket of warm milk.
This is the formula we use to find the mean. The large E-shaped character is the Greek uppercase letter sigma, which usually tells us to take the sum of a bunch of numbers. Sigma will be used throughout the video, so be sure you understand it before moving along. Essentially, sigma equals summation.
The I equals 1 indicates to begin the sigma summation with the first value of the data set. If the formula were to say I equals 2, then we would begin the summation with the second value of the set. The lowercase n indicates the number of values in the set.
X sub I looks pretty tricky, but it's actually pretty simple. Big X stands for the values in the data set. Lowercase I again tells us what value in the data set to begin with. Remember, that's the same thing I meant when it was paired up with that giant E, sigma. X sub I basically tells us to use all the numbers in the data set beginning with the I value. It means pretty much the same thing as sigma sub I. The difference is that X sub I tells us what part of the data set to use. Sigma sub I tells us what value in the data set to start adding with.
Once you have all the values in place, to find the mean, simply add up all the numbers, then divide the summation by n, the number of values in the set. Remember, if I equals 1, the summation begins with the first value of the set and ends with the nth value.
When looking at this formula, it's important to remember that most of these symbols are not actually involved with the calculations. This is what makes statistics different from calculus or algebra. In calculus and algebra, when we use a formula, we are trying to solve for variables. Take a look.
In this equation, the variable we solve for can change from problem to problem. If this were algebra, we could solve for any one of 4 variables in this problem: y, m, x, or b.
But statistics is different. When we have an equation for something like the mean formula, even though there are a number of variables in the equation, there's only one that we will ever have to solve for. In the case of the mean formula, that variable is x bar. The other symbols, like I equals 1, are there to describe what parts of the data set to use. Think of them as kind of like mathematical adjectives. These adjectives make up the recipe that will help us find the mean once we plug in the proper numbers.
To help you better understand this formula, let's strip those adjectives away and take a look at the formula's basic function.
Let's take out the i's and replace the sigma with what it is, a plus sign. The variables that indicate the numbers we're using are x, which tells you to use the data set, and n, which represents the number of values in the data set. Once you've got those, technically you've got everything you need to find the mean.
When we put the adjectives back in, the I equals 1 tells us what value in our data set to start with. So we take its advice, start with the first value in the set, and add up the values in the data set. Divide that sum by n, and you've got yourself your mean.
Now, that formula has a lot of funky stuff, what with all them X's and I's and all. But when it comes down to it, if you remember to take all the values in your data set, add them up, and divide by the number of values in the set, you should be able to find the mean no matter where you are or who you're with, even if you're in the Yukon Territory with a rhino and my Aunt Phyllis.
If you want a shorthand way to remember the formula for finding a sample mean, just remember that x bar equals sigma of x over n, and you should be okay. Sigma of x just means add up all the values in the data set and then divide by n, the total number of values in the data set.
Let's see how it works using our example of the 12 martyrs and their walking distances.
Since I equals 1, we start with the first value of the data set. N equals 12 because there are 12 values in our data set. X sub I will consist of all 12 values in our data set.
We plug in the values and find sigma, the summation, which in this case equals 145. Divide that by n, 12, and you get 12.083. Let's go with one significant digit to the right of the decimal place and round that up to 12.1. That's the mean of our data set.
So do you see what we just did? We just spent 10 minutes telling you how to find the average. Only statisticians try to make it look really complicated by throwing in sigmas and x's and stuff. Don't let them throw you. Just remember that sigma is there to remind you to add, and x is there to remind you to use the values from your data set. And those little i's, they just tell you which value in your data set to start with. And n is just the number of values in your data set. No big deal, right?
All right. After the mean, the next measure of central tendency is known as the median. The median is identified by a lowercase m and is the measurement that falls in the middle position when the data is ranked in order from smallest to largest. Remember, median equals middle.
Just like the median strip runs right down the middle of a road.
Okay, take a look here. There are 5 salami sandwiches here in a row, from the largest sandwich to the smallest sandwich. I know these aren't numbers, but this is just to illustrate a point. The median of these salami sandwiches is this sandwich because it's the middle position at the 3rd ranking. That's all the median is. It's just the middle value in a group of values.
There are 2 different ways to find the median, depending on the number of values you have in your data set. We'll show you both.
If the total number of values in the set is even, you still line up all the measurements. Only this time, the median is halfway between the 2 middle measurements.
For our walking distance example, we have 12 values. That's an even number, so the median is halfway between the 2 middle measurements. That means the median would be between 11 and 12, which are the 6th and 7th values of the set, respectively. So the median of this data set is 11.5.
Okay, so that's the median. The third measure of central tendency is called the mode. The mode is the measurement that occurs most often in the set of data. Let's go back to the grumpy men.
As you can see in our original data set, there is one measurement that occurs more often than the others. That measurement is 6, and it's the mode, or the most frequently occurring value in our data set.
Be aware that all data sets are different, and there can be more than one mode or no mode at all.
Got that? The first numerical method is measures of central tendency. There are 3 measures of central tendency that help us locate the center of our data: mean, median, and mode. The mean is the average of the data set. The median is the middle value in the data set. The mode is the most frequently occurring value in the data set.
So that was the first numerical method for analyzing data, measures of central tendency. Now let's look at the second.
Measures of variability.
Measures of variability are the second type of numerical representation. These measures tell us about the dispersion of the data set. In other words, they let us know how spread out it is. There are 4 measures of variability: range, deviation, variance, and standard deviation. The first and the simplest is called the range of the data set. This time we won't be using the range to make classes or anything. We just want to show you what it does on its own.
The range gives us the big picture on how spread out our data set is because it tells us how far the values in our data set stretch from the high end to the low end.
In our martyr example, we subtracted our lowest walking distance, 2, from our highest walking distance, 23, giving us a range of 21. This tells us the big picture of how spread out our data is.
The second measure of variability is deviation.
Deviation is how far away a measurement is from the mean or average of the set. So it tells us how much a value deviates from the average.
The formula for calculating the deviation of a measurement x is x minus x bar. Don't forget that x bar represents the mean of a sample. Every value in the data set, or x, has a deviation from the mean, so x can be any value in our data set.
Let's take the lowest value in our walking martyr data set and find its deviation. The lowest value, which we'll use for x, is 2. The mean, or x-bar, is 12.1. Remember, we found the mean for our Grumpy Men data set by adding up all the values from the set and dividing by n, the number of values in the set.
So, to find how far our first value of 2 deviates from the mean, subtract the mean, 12.1, from 2, and you get negative 10.1. You see what we just did? We subtracted x bar, the mean, from x the value.
Now let's do another one, this time using the highest value. We subtract the mean, 12.1, from our value of 23, and we get a deviation of 10.9, which tells us how far the value 23 is from the mean.
The third measure of variability is called variance. The third planet from the Sun is called Earth. Coincidence?
When we discussed finding the mean for populations and samples, we saw how the mean has different symbols depending on whether it's the mean of a population or the mean of a sample. If we're finding the mean of a population, we used mu. If we're finding the mean of a sample, we use x bar.
Variance works the same way. The variance of a population and the variance of a sample are also represented by different symbols.
But unlike the means for a sample and a population, the variance for samples and populations are calculated in slightly different ways.
That's not too hard to remember, right? The method for calculating variance varies depending on whether you're working with a sample or a population.
The variance of a population is designated by the lowercase Greek letter sigma squared. To find the variance of a population, or sigma squared, the first thing we need to do is find the deviation for each value in our data set. Remember how to do that? It's just x minus mu. Do that for each value in the data set. Then, take the deviations of all the values in the data set and square them. Then take the squares and add them together. Divide by n, the number of measurements in the population, and you've got your variance. It's essentially the mean of the squared deviations.
We know we can find data from a sample and apply our observations to the population as a whole. Well, you can do the same thing with variance. We can use the variance of a sample to estimate the variance of the population. We just showed you how to find sigma squared, the variance of a population. But as we said, to find the variance of a sample, however, we have to use a slightly different formula.
Here's what you do to find the variance of a sample. Sample variance is designated as lowercase s squared. That's easy to remember because sample starts with s. Just think sample, s. The variance of a sample is equal to the sum of the squares of the deviations divided by n, the sample size, minus 1. The only difference from the population formula is that we subtract 1 from the number of values in the set.
To find out why n minus 1 works, statisticians use a complex mathematical concept that is beyond the scope of most basic statistics classes. So we won't go into great detail. Just know that the sample variance can be used to estimate the population variance.
The sample variance only tells us how much the measurements in our sample vary around the sample mean. But we can use it to get a general idea of how the measurements in the population vary around the population mean. By subtracting 1, the sample variance is a more accurate estimate of the population variance.
There's another component of variance that tastes a little fudgy. It's fudgy because we use the squares of the deviations and not the deviations themselves. Take a look at this distribution curve.
As usual, the curve is centered around the mean. Since deviation is found by subtracting the mean from a value of x, all the x values that are less than the mean will have a negative deviation. This will cause problems when we add up the deviations to find the variance. That's because whether our data set is symmetrical or not, if we add the deviations up, they'd cancel each other out and give us a variance of 0.
I know it's crazy, but it's true.
By taking the deviations and squaring them, we get positive values, and we avoid the mess caused by working with negative deviations. That's because a negative times a negative is always a positive.
Statistics! To help grasp the idea of variance a little bit better, let's assume that our set of walking distances is a sample from a larger population and find the variance of our data set. Because we're assuming it's a sample, that means we'll use the sample variance formula.
Again, here's the formula we use to find the variance for our sample. The first thing we need to do is find the deviation for each value in our data set. To do this, take each value x and subtract the mean x bar. Remember, a while back we figured out that the mean of our sample x bar is 12.1.
Plug in our first value, 2, and we get a deviation of negative 10.1. If we take our second value, 5, and subtract the mean, we get negative 7.1. Do this for each value of x. Once you've found all the deviations, square them, then find the sum of the squares.
Unfortunately, there's not an easier way to do that, so get used to squaring.
Square your partner do-si-do. When you find the variance, it's the only way to go.
We take the squares, add them together, and we get 522.92. Once we've done that, we can find the bottom line. Take n, the number of values in the data set, and subtract 1. 12 minus 1 equals 11. Now, take 11 and divide it into the sum of the squares, 522.92, and we get 47.54, which is the variance of our data set.
The variance gives us a general idea of how much our figures are spread out around the average.
Logically, having a variance of 47.54 when the highest value in our data set is 23 may not make a lot of sense to some of you. Well, don't worry.
The variance doesn't mean a whole lot on its own, but it comes in real handy when we find the standard deviation, which we'll do in a second. So just remember that the variance doesn't have to make sense, it's just the means to an end.
Now that you have a handle on finding the variance, let's move on to the fourth and final measure of variability, standard deviation.
The standard deviation is equal to the positive square root of the variance.
Like mean and variance, the standard deviation has a different symbol depending on whether we're working with a population or a sample.
Since standard deviation is related to variance, we use similar symbols for each. Since the variance of a population is represented by lowercase sigma squared, the population's standard deviation is represented by lowercase sigma.
Likewise, since the variance of a sample is represented by lowercase s squared, the standard deviation of a sample is represented simply by lowercase s. This makes sense because the standard deviation is the positive square root of the variance. The variance of a sample is s squared. When you take the square root of s squared, you get s, which is the standard deviation of a sample.
To help you keep these symbols straight, think of it kind of like this.
In a casino, you have big-time players and you have small-time players. Mu and Sigma are big-time players. They run with the population and hang out at the high wager tables.
X bar and S are small-time players. They hang out with the samples.
Now let's see some of these symbols in action and find the standard deviation for our distance example.
Remember, we're treating our walking martyrs like a sample.
Thanks a lot!
The variance we found earlier, s squared, was 47.54. To find the standard deviation s, all you have to do is take the positive square root of 47.54. That way, we're compensating for squaring the deviations earlier. Do that, and we get 6.89, which is the standard deviation for our snow walking martyrs. Remember, the standard deviation is like a guidance counselor. It's always positive.
So, I bet you're wondering, just what is this standard deviation, aside from a statistic that uses a lot of other statistics to find it? Well, think of the standard deviation as a unit of measurement, like an inch or a nautical mile.
The standard deviation tells us where measurements in the data set lie in relation to the mean. Even though there may not be a measurement that lies 6.89 units from the mean, think of it like 6.89 is the average deviation for a value in our data set. By finding an average deviation, it helps us see where values lie in relation to one another.
Values that are very large or very small may be several standard deviations from the mean. Those close to the mean will be only 1 or 2 standard deviations away. In general, most measurements should fall within 1 or 2 standard deviations from the mean.
Each dataset has its own mean, and each dataset also has its own standard deviation. So, one standard deviation will be a different size for each dataset.
For instance, if we look at this conversion chart in our martyr example, one standard deviation is equal to 6.89 miles. If we had taken a sample of the martyr's ages, one standard deviation might be equal to 5 years.
However, no matter what kind of units our distribution is working with, be it miles, years, or even the number of shanties in your local shanty town, the number of measurements that fall within 1, 2, or 3 standard deviations from the mean is the same, as long as we're working with a normal curve. This is all explained by something called the empirical rule, which we'll tell you about in a second.
Because the deviation is standardized, it gives us a way to see how measurements fall in relationship to one another. Here's an example.
Say Mark and Carrie commute from Boston to Hartford every day. Not the most rational of commutes, but it works for the sake of our example. Boston to Hartford is their standard commute. One day, their company moves its office to Washington, D.C. Mark and Carrie have a really cool place in Boston, so they don't want to leave. Washington is 9 times further away from Boston than Hartford, so their new commute will be equal to 9 standard commutes. When you think about it, standard deviation works a lot like an old-world style of measurement.
Honey, your father's taken the mule, so I'm afraid you'll have to walk to your apprenticeship.
But that's over 3 barrels and a rivulet away!
Don't be a wuss.
Unlike rivulets, the standard deviation is a good measure of variability because it indicates where measurements lie on the x-axis. Because of that, the standard deviation will play a big part in constructing our distribution curve. Remember that, puppy? What happens is, the smaller the standard deviation, the narrower the curve. The larger the standard deviation, the wider the curve.
Now that you know how to calculate all these statistics, mean, range, and deviation, we can start showing you how they're used in a more practical way. We'll start by looking at how they work their way into the distribution curve.
Okay, here's what a normal distribution looks like. In all normal distributions, approximately 68% of the measurements are within plus or minus 1 standard deviation from the mean.
Another way of stating this is that 34% of the measurements are within 1 standard deviation to the right of the mean, and 34% are within 1 standard deviation to the left of the mean.
Keep in mind that just because some measurements are to the left of the mean does not tell us they have a negative standard deviation, because negative standard deviations are not allowed. It just tells us they're to the left of the mean. In fact, if a measurement lies to the left of the mean, we know that measurement is below average. If a measurement lies to the right of the mean, we know it's above average.
In addition, in every normal distribution, 95% of the measurements in the dataset are within plus or minus 2 standard deviations from the mean. And almost all of the measurements in a normal distribution are within plus or minus 3 standard deviations of the mean.
This is one of the fundamentals of statistics and is known as the empirical rule. The empirical rule states that nearly every measurement in your distribution is within plus or minus 3 standard deviations from the mean. There is an exception to this rule known as an outlier. Remember them? We mentioned them a long time ago. Outliers are statistics that lie dramatically far away from the mean.
So let's take the empirical rule and apply it to our martyr example.
Our martyr example isn't normally distributed, so technically the empirical rule doesn't apply. But hey, that doesn't do you any good, so we're going to see what the empirical rule would tell us about the martyrs if our distribution were normally distributed, like this. Check it out. The mean walking distance for our snowbound martyrs is 12.1. The standard deviation is 6.89. The empirical rule states that 68% of the measurements are within 1 standard deviation from the mean. So if we apply the empirical rule to our martyr example, we can say that a majority of our martyrs walked over 5.21 miles, but less than 18.9 miles.
Again, there are 4 measures of variability that tell us how spread out the data is: range, deviation, variance, and standard deviation. Range tells us the span of our data set from lowest value to highest value. Deviation tells us how each measurement deviates from the mean. To find it, subtract x bar from x. Variance tells us how the data set as a whole is spread around the mean. To find the variance of a population, take each deviation, square it, add the squares up, and divide by the n the number of values in the data set. If you're working with a sample, divide by n minus 1.
Standard deviation gives us a standardized unit that tells us how far away each measurement is from the mean. To find standard deviation for a sample or a population, just take the square root of the variance. The empirical rule states that in a normal distribution, 68% of the measurements will fall within one standard deviation of the mean. 95% of the measurements will fall within 2 standard deviations of the mean, and almost all of the measurements will fall within 3 standard deviations of the mean.
So far, we've seen 2 numerical methods for analyzing data, measures of central tendency and measures of variability.
Measures of relative standing.
The third numerical method is called measures of relative standing. When we discuss statistics in terms of their relationship with other values in the data set, we're talking about relative standing.
Relative standing simply means that we are comparing 2 variables to one another.
Kind of like how class rank is a way of comparing different GPAs. We'll discuss 3 measures of relative standing, including outliers.
The first measure of relative standing is called the z-score. The z-score tells us how many standard deviations a measurement is away from the mean.
Finding z-score is relatively easy. To find z-score, all you need to do is take x, any of the values in the data set, subtract the mean, and divide by the standard deviation. So if you're working with a sample, take x, any of the values in the data set, and subtract the mean, x bar. Then divide by the standard deviation, s. If you're working with a population, take x, any value in the data set, subtract the mean, mu, and divide by the standard deviation, sigma. So if you're working with a sample or a population, the calculations stay the same, it's just the symbols that change. Essentially, to find z-score, all you have to do is divide the deviation by the standard deviation.
For example, say that there are 2 classes taking a stat course from the same professor. On the midterm exam, the distribution of the exam scores for Section 1 has a mean of 75 and a standard deviation of 5.
That means that the average score was 75, and that according to the empirical rule, a majority of students scored over 70 but less than 80. In Section 2, the scores also have a mean of 75, but the standard deviation is 7. So most people scored between 68 and 82.
Meet Riva. Riva is in the first stat section. Riva got an 85 on her statistics test.
Now meet Wendy. Wendy is in the second section. Wendy got an 85 on her statistics test.
Riva and Wendy want to find out who got a higher grade on the statistics test. Both of them got an 85, but they're both in different sections. So to see who did better, we can use z-score to see whose 85 is higher above the average for her section.
In Section 1, the z-score for an 85 is 2.0. We got this by subtracting 75, the mean, from 85, the x value, to give us a deviation of 10. Then we divided by 5, the standard deviation, giving us a z-score of 2.0.
For Section 2, we use the same method to find the z-score and divide the deviation, 10, by the standard deviation, 7. So, we find that a grade of 85 produces a z-score of 1.43.
So now that we have the z-scores, how do we know who did better on the test?
Well, mean is the same thing as average, right? Z-score tells us how many standard deviations a measurement is from the mean.
A measurement with a z-score of 2.0 is further away from the mean than a measurement with a z-score of 1.43. So, the measurement with the higher z-score is more standard deviations away from the mean, and therefore higher above average. Whichever score of 85 translates to a higher z-score is higher above average, and therefore a better score.
In Section 1, our z-score was 2.0, and in Section 2, it was 1.43. 2.0 is higher than 1.43, so we can say that Riva's score of 85 in Section 1 is higher above average than Wendy's score of 85 in Section 2.
That means that Riva got a better score.
According to the empirical rule, most or all of the measurements in any distribution curve should be within 3 standard deviations of the mean on either side. Or, in other words, most measurements should wind up with a z-score of 3 or less. A measurement with a z-score greater than 3 qualifies as an outlier. Obviously, we call it an outlier because it lies outside of the normally expected area.
Also, it may help you to understand that an outlier is either very large or very small in relation to the other measurements.
Remember in our martyr example when we threw the value 4,806 out of the data set? That was a perfect example of an outlier.
We got rid of that outlier when we found the mean for our histogram. Since it's so extreme, an outlier can bring the average way up or way down.
For instance, if we toss 4,806 back in our data set of walking distances, the mean shoots way up to 380. Because that average is so bloated, it doesn't really tell us where the middle of our data set is.
When this happens, the median makes for a great remedy to remove the effect of an outlier.
The median of the set is the middle value, which in this case is 12. 12 makes for a much more accurate picture of the center of the data set than 380.
Remember, the mean we found when we threw out the value 4,806 was 12.1, so you can see why we ditched it.
While we tell you about the second measure of relative standing, think back to when you took the SATs. When you got your scores back, the sheet told you what they were, and it also told you what percentile those scores fell into, or what percentage of students you scored higher than. The percentile is another measure of relative standing.
So, say your SAT scores fell in the 60th percentile. If you have 10 friends, rest assured that you're smarter than 6 of them.
To separate data, statisticians commonly use the 25th, 50th, and 75th percentiles, which are usually called quartiles because they separate the data into 4 quarters, like a pound of butter.
Let's say that under this curve, areas A, B, C, and D are all equal. That means they contain the same number of measurements. Area A contains values that fall in the 1st through 25th percentiles. Area B contains values that fall in the 26th through 50th percentiles. Area C contains values that fall in the 51st through 75th percentiles, and Area D contains values that fall in the 76th through 99.9th percentiles.
We'd go ahead and say an even 100, but it'd be pretty hard to do better than yourself.
When we divide a curve into quartiles, each quartile, A, B, C, and D, contains 25% of the total values in the dataset. That means that each quartile has an area of 0.25. Notice how if you add up all the areas, you get 1.
We just looked at the 3 measures of relative standing: z-score, outliers, and percentiles. Z-score tells us how many standard deviations a measurement falls from the mean. To find it, divide the deviation by the standard deviation. An outlier is a measurement that falls beyond 3 standard deviations from the mean. In general, measures of relative standing tell us how measurements fall in relation to one another. Percentiles rank measurements by percentage, so we can pick a specific measurement and see what percentage of the other measurements it's greater than.
You've just witnessed 3 different types of numerical methods for displaying data: measures of central tendency, measures of variability, and measures of relative standing. The first type, measures of central tendency, includes mean, median, and mode. They help us locate the center of our data set. The second type, measures of variability, includes range, deviation, variance, and standard deviation. The third type, measures of relative standing, includes z-score, outliers, and percentiles. Well, looks like we're just about finished. Whoa, hey, don't cry. We accomplished a lot. We looked at what statistics is. We set up and solved statistical problems, amassed data sets. Remember the histograms we made? Then we checked out those distribution curves and made some stem and leaf displays. Oh, man. Oh, well, what about all those numerical methods? Remember doing all those measures of central tendency, measures of variability, and measures of relative standing? Oh, man. We were kings then. But there comes a time in everyone's life when you just have to let go. If you're really suffering, pick up the High Stakes World of Statistics Part 2 and 3, or any of our tapes, basic math, psychology. We're always making more. And you can always call us at 1-800-238-9669.
the positive square root of the variance.
Erica, to try our Fuzzy Dice Soda Cola. This Fuzzy Dice Soda. It's a cola.
We'll still use more or less the same concepts.
Which measures.
Which measure.
Where are we going with this?
Oh, no.
What's gonna happen?
Pull on my mouth. Hi, I'm Don Most. Welcome.
Instagram. The boa was. Don't be a wuss.
But, oh, look, I won! Hey, hey!
Left of a mean, we left of a the.